Good evening, sir.
Just let me present my screen, then we'll start the session. Okay.
Sir, actually, I wanted to ask, will you be taking doubts or just concept clearing?
So it will be both kind of like it will be doubt clearing and the concept clearing both will happen. Okay.
Okay, sir.
In the last session, both of you have done the till Dijkstra algorithm. No? So this time we will see a Belmont and uh, will give a brief. Let me present my screen. Then
Okay, sir. Okay.
things will start. And please, everyone, raise your hand so that I know, so that I can know your doubts. Hope my screen is visible to all of you, right?
Yes, sir. It is well.
Okay. Just a minute.
Hello, sir.
Yeah.
Sir, will you go through each and every topic of the week 11?
So last time till we did right. Last time Vishal have taken until the extra algorithm. We did right. So first thing I want to let you know how many of you went through this open session and solve it as session. Anyone have
Session which was taken yesterday in the morning.
No. It is available in the portal, the older session.
Yes, sir. I went through this open session.
This open session, no, there you have seen. So this is open and solve. There are
Actually,
two.
it had a graded assignment question also.
Yes. So in this session, you will very in brief, you will see the Warcel algorithm, that is Freud Warcel algorithm. So
Sir, can we get this PDF of this open session, sir, for this one, especially this Venkateshan and yeah, on this one and the earlier week also there is one open session by Venkateshan. It is given in this portal itself.
okay, so yeah, I will try to give this PDF. Okay, I will try to upload this session's PDF. So in this session, I am showing you this session because.
Hello, sir.
Yeah, just a minute. Floyd Warcel algorithm is discussed. So in this session, in a very nicely, if you want to see how the Floyd Warcel algorithm is how will proceed. So that's why at least in this session, I'm not going to discuss this. I will take your doubt based on that. I'm not going to discuss that Floyd Warcel algorithm. The reason is, if you see in this video, it is very like once I will start, it will take the whole time. Okay, I will discuss the others like this Kruskal and Prism algorithm and this one that Belmont, that whatever the Belmont is there for the shortest path. And these we will discuss. This Floyd Warcel algorithm, I'm not going to, means I will not give the brief of it, how we'll proceed, because here if you see that in this session, it is very nicely have discussed, very nicely. Every and each topic have discussed, like how you will make a adjacency matrix or how we will do this algorithm. That is very nicely. And actually, if you see that, that's why the whole session, if you see the whole timing is 2 hours. This session took only while discussing the Floyd Warcel algorithm. So if you, I'm just suggesting you, please watch this session, it is a very useful if you want to know the Floyd Warshel algorithm. That's why it is already in the portal. It is always kept purposely to know that what is that algorithm. Okay. Just
From where we have to start?
just a minute. Okay, just a minute.
So, what will you be doing today?
Just a minute. We'll do a doubt session first, and then we'll do a. I'm just that whatever the remaining thing, except the last session, with till extra we did. So Belmont will try to do, and then Prism and that Kruskal I will discuss, and some I will give some this. I will give some brief in this Floyd Warshel algorithm. Okay, in this session we try to do that. Am I audible?
Yes, sir.
Okay.
Yes.
Okay. Yeah. Just a minute. So, so in the last session, we did the extra algorithm. What is that? That is the way to find. Am I audible?
Yes, sir.
Properly.
Yes. No, sir.
Am I audible?
Yes, sir.
So will you be
Okay.
clearing the doubts first?
So please
Voice is breaking.
let
Sir, your voice is not proper actually. It's breaking.
first I will take your doubt.
Your voice is breaking.
Sir, your voice is
So
not proper.
what
It's jarring.
doubt, please raise your hand so that I know your doubts. Okay. Yes. Yeah. Hi. Sir, am I audible right now?
Yes, sir.
Am I audible? Okay.
Yes, yes.
Yes.
Okay. So yes, Region, what's your doubt?
Sir, I had a doubt in 11.8, question number 3.
Okay, 11.8. So what's your doubt here?
Sir, I don't know how to approach it because there can be many ways for this graph. So how should we know? Like, is there any
So
formula kind of thing?
No, so there is no formula. You have to do manually. That's the one thing.
Sir, the answer
So
is, I
like
guess,
you have
64.
to do manually.
Okay, I
Okay,
thought
the
it was-
answer is 64 is given.
Yes, sir, I guess it's 64.
Okay, just a minute. Not 64, it is a 16 only.
Okay, okay. So like we'll have to check
Yes.
from every node.
Yes, you have to. There is no nothing. You have the trees. It actually the possible. The spanning tree are possible in the graph. So the way is only that you have to do the manually.
Okay.
That's the one
Thank you, sir.
part. Yeah. Yes, region is done. Mayank Bharti, what's your
So
doubt?
is the discussion for the
Yes.
entire week 7 over?
Yeah, but it is within like one. Mayank is only. Yes, Mayank, what's your doubt?
Yes, sir. I have doubt in 11.5 question 1.
11.5. Question 1. Okay. So what's your doubt here?
Actually, I'm getting answer as 9 minutes and the correct answer is 8 minutes. So where I'm going wrong, I'm unable to find it because I've done it twice also, but the same answer is coming.
Okay, so ABCD is there, the nearest Himalaya at the time 0. Okay. Weight of each vertices, the time in minute by the okay. At watch time, the city G start flooding.
Yes, sir.
So at the time 0 minute, the city B completely flooded. Okay, here is B. Shah gave flood warning to the cities these and which are near to the foothills of vertices represent the cities and edges represent the how many cities are connected. So you have to do here is no that shortest path you have to find.
Single source shortest path.
Yeah, single source shortest find. So here is you can see this is a you can use the Dijkstra algorithm, no? So
Yeah,
what is
yeah.
that? Going through C, once you go 3 C and then A, because if you go any other, so this will now this is a 14 is given. If it is a direct is going, so this is a 14-minute will take. But if you go with the B and then C, okay, this is the minimum. We single shortest path. If you go from C and then A, okay, then from A, so you have to see which one is going to be minimum, right? So this is, if you see that directly, if you can reach, which is 1, 2, and this is 1 and 2, 3, and this 4 we have done. And then finally, if you see that this is, it will reach to the, if you come to here, it will be 8. Very
Can you just
quickly.
perform the algorithm on this question just for one time?
So Dijkstra, if you perform this Belmont also, it will work.
Yeah,
Or
but
the Dijkstra is
I just wanted to
what
see.
is the Dijkstra algorithm? Dijkstra algorithm is to like. So what is that? If you see the in the algorithm, that is a burning thing, no? If we start burning, or here is the flooding thing is start flood. It is at 0 minute it flooded, completely flooded. And then the water will start from moving in the direction of A, and we start moving in the right direction of G. So it took 14 minutes and it is 4 minutes. So this is the algorithm. No, if you from here to here, it will 1 minute will take. Then here within 3 minutes by the route of C and A, it will take 3 minutes. But by the route of direct to A, it took 4 minutes. So once it start reaching, am I audible?
Yes, sir. Yes, sir.
So once you start reaching to A, if you see that by the route C or by the city C, it reaches within the 3 minutes or after the 3 minutes, but via the direct edge, like here, which took 4 minutes. So after 4 minutes, it in the direction of like in the direction of city D, F, and E. So to city E, it took 10 minutes, but and then after it will take 11 minutes. But once it will start to moving A, after 1 minute, the city F will be flooded. Okay, and here after 1 minute, the D city will be flooded.
Okay,
So
sir. Okay, sir. I'll try
from
to.
D.
8 minutes is the answer, sir.
It will start moving like this and this side. So this is the algorithm. No, this is the Dijkstra algorithm. And here is Belmont says if it is any positive or negative, for that you have to make a, am I audible?
Yes, sir. Yes.
Am I audible?
Yes, sir. Yes, sir.
Yes,
But
sir.
So, and in the case of Belmont, okay, in the case of Belmont Ford algorithm, you have to start, so we'll discuss that. So this is whatever I just now discussed, that is because of the positive route, we don't need the update here. We just need to go with the minimum and go which direction would be good. And this is the Dijkstra algorithm says. But once we have the negative is, so there is a problem to know which will give the minimum or how will do a better performance. So there is a Belmont. Once you have the single source shortest path, the Belmont, if you have the negative weight, then in that case, if you go with the Belmont Ford algorithm, that would be good, because Dijkstra is the only for the positive weight edge. Sorry, edges of positive weight, right? So that is a good question we just now. So this is the question. This is the Dijkstra algorithm. Just now I said like by which route I will go like this and this and this. Okay, this is the way. If you see that, that's
Sir,
if you gone through the lecture, that what is the,
excuse me,
sorry?
sir.
Yes.
So answer for this question may be B to C, C to A, and A to F, and F to G, right, sir?
Yes,
That will be A to, which is minimum.
yes, yes. Yes. So yeah, we just now discussed the Dijkstra algorithm. So this is the Dijkstra algorithm. This is the way to
Thank-
go, or this is the Dijkstra algorithm. Like once we'll start from B and then C, and then you. That's the process. Like the flooded will start or burning will start from here to which way in the, which route it will take to move. Okay, along that it will go here.
And sir,
Yes.
is it applicable for only for undirected graph or both directed and
Even the
undirected?
directed graph will know. Even the see, this is the it will be work for both undirected and directed. How the direction is given in that the burning is will start, no?
Okay. Okay, sir.
Sir,
Huh.
sir, actually, have you like has the summary been explained, sir? Because I think I missed few sessions and now I joined lately only. Like summary of
So
week.
here, like whatever I am just going to do, that is, we will, because if you see the last session have done with the transitive closure and the longest path, okay, longest path transitive closure until the Dijkstra have done Dijkstra algorithm. I will start from the Belmont. So before to recap that, we can see that what is those all. The longest path is, let me start with that. So very quickly we can recap and then we can start the other algorithms. So the first in week 11, the first thing is longest path. So longest, the purposely what is the longest path is here, or when we'll do the, on which graph we are able to do this or to find the longest path is on the DAG. DAG means directed acyclic graph. So what is that directed acyclic graph means? There will be like a graph which will be a directed graph, okay? There will be direction, but in that graph there will be no cycle. That is called DAG, okay? So suppose here is, if you make it, suppose here is A, B, and C is here. C and D is here, and E is here. And F is here. So direction is like this, and then this, and then this. And here is one. This is we have, and this is. So see, it is what is happening if I will make like this here. If I will make like this, so it is a cycle. See that this is not. If I will make like this in this direction, so this is a cycle. This is not a DAG. This is a directed, but it is a cyclic graph. Here is in that there is a cycle. So this is not a DAG. If you make like this, the direction is like this. Then this is, if you see that this is not a DAG. So this is the same direction. Is this in the direction? So if you see that this is there is no cycle in that. So this is the DAG here we have. Now what is the longest path is, what is going to be the longest path in this graph? So whatever we have we have seen for the topological sorting. So in the DAG, there are two concepts, or there are two things we'll try to do. So what is the DAG here? Here is one important, that suppose you want to, in the course as example, if you want to do this course where is this B is, and you are donating C or D, E, and here is, let's say this is F, this is G. So if this is, you have the courses like B, C, E, F, these are the courses. So if you want to do the G course, so which course is needed to finish at least the G course? So this is the purposely, this is the mean of DAG. Actually, this tells you the dependency of the courses. Like somebody want to complete the course G, so he have to complete first A and then B and then E and then G. Like this he have to perform. And so that is called the topological sorting, like in which order you have to complete. That is the use of the, you can say, the topological sorting. And what is the DAG means? How much time it will take to complete that course. Is there any that longest path is means if you want to complete this course G, so by which route or by which way if you go so that he able to complete? And what is that? What is going to be the longest way of, you can say, longest path? That is the purposely, that is the name it is given, that longest means which way he will go so that he able to complete that course G. Like if you want to hear the longest path, so what is the process? Last time we have discussed that you have to write the in degree and out degree. So here is in a DAG, there is one thing it is given that in a DAG, there will be at least one vertex which have in degree 0. Like here A have in degree 0. What is in degree means? Coming edges. Here in degree of A is 0. Here is in degree of B is 1. Here is in degree of C is 1. Here is in degree of E is 1 also. Here is also 1. Here is in degree is 1. Here is in degree of F is 3. Right? 3 incoming edges are here. Here in degree of F is 4. Sorry, here is 3 also.
3. Yeah.
So now if you start topological sorting, so what you can do, like you can start which have 0 degree, in 0 in degree. So you will start from A. So let's make it a sequence. Like I took A and now start removing the which have in degree 0. Like if you remove A here, okay, so if you remove A, so update the in degree of related to. So now in degree of B become 0, in degree of C become 0, and in degree of F become, if you remove from 3 to 1, it will become 2. Now which have the degree 0, so either you can choose B and C. Let's choose B here. So if you choose B, then let's remove that B. So if you remove B, so in degree of E become 0 here now. And here is, along with that, we can write the sorted as this longest path also. So longest path here is, I just remove the first A and then from A we B we did, okay, so B once we remove the B, and then again the in degree of E becomes 0, we remove the B here now. So either you can choose B and B or E. So either you can write like C, or you can write E also. So let's do here E. Okay, so we can, if you will choose E, okay. If you choose E here, so here is in degree. If you remove this, then it will become, here is 1, and here is what it will become? It will become 2. The updated, we have updated the in degrees of G. Okay, so here is now, once we did E, so and in the longest part, this is going to be E. Okay, now so if you see that here is 0 have in degree of the vertex is, now this is a DAG. So in that 0, sorry, C have the 0 degree. So now once you can remove C now, okay. So here we chooses E. Now there is no, we cannot write like this. No, just a minute. Let me confirm it. So just a minute. Here is the order, and here is the longest path is theory, topological order, and here is the longest path is given. So I just removed to here I did not give the longest path here. Okay. So this, yeah, I just started blindly doing this one. Here is this order is actually okay. Here is the longest path means at 0. I just whatever the in degree I just wrote here along with that we can I need to write that what is the longest from 0 to longest path. So that is need to be right like this. So here is B and here is C and it is F. Sorry. Okay, so here is the in degree of A 0 and the longest path we started which have the 0 in degree. No, so longest path we will start it from here is, so longest path A to A is 0, and here is from A to longest path is, if you start doing that, longest path here is 1, and okay, from here to this one is longest path, the in degree of here is 1 and longest path is 1. Here is in degree of C is 1 and the longest path is what is the whatever the previous one which is updated that. So here is in starting each have the degrees, each have that will be 0, no? So here will be 0, here will be 0 if you see that. So what is that? Either you can go with the so topological sorting by this way, or the longest path, either you can choose like this. Either you can see the from the graph itself, like from A to B and from B to C and then C to G, and any other way, which is going to be the longest path for A to G. From G to we cannot go any other place, or if you move to E, then from E we can move this one, and this one, and this one. Then to G. So this is 1, this is 2, this is 3, and this 4. Previously it was 1, 2, and directly 3. So you see the longest path from F we will go, then we have the longest path. So A to B and then C and then F and then G. A to B, A, B, and then C and then F, G. 2, 3, 4. So either by this way, if you go, that this is going to be the longest path. So if you go with the algorithm, if you see that is there written, you need to write the in degrees, and in starting, if you start that is going to be 0, 0. The longest path each will be 0. So if you see that this is the one algorithm to find the longest path. So whatever the order, if you have while doing the topological sorting with the same algorithm, you just need to record that. If you remove that, then here will be the longest path. If you remove this A, so this will become 1
You
here,
have to
and
keep
in
removing
degree,
the vertices with in degree zeros.
in degree will be updated and longest path will be also updated. So this is the way to whatever the topological sorting, if you are doing in the same order, you need to update the longest path of the particular vertex. And then now here, if you remove this B, then here it will be what? The longest path is 1 previously for B. So here will be, so here is the record. You can write like for A, it will be longest path 0. For B, longest path is 1. And then we remove C, no? So we remove, I think I have missed something is that I'm missing. I think C is here and C is somewhere. Okay. E is, no. Here is, this one is E. So for E, what it will be, once you remove that, then 1 will be added 1. So here for E, it will be 2. And for C, the longest path will be 1. Once you remove that, it will be updated. And then for D, what will be? This will become, then this is topological order, order, and this is going to be, once you remove C, and this will become again C, and for D it will be in degrees 1, and the topological order, sorry, longest path were 0, so 1 plus 1 it will become 2. So for D it will be 2. So finally, so by this way, this is going to be the path to show, and finally which is going to be the most one, and you have to record that, that is the matching, like from A to B, and then E, then F, and then C, and this is the G. If you see that, if you see the algorithm, no, it will be very much clear too that how we will proceed. Okay. So this is the way to find the longest path and shortest path. Even if you, while looking the graph, you can find like which is going to be longest path. Just now I tried, no, I just tried.
For C and G, can you just explain how did you get 2, sir? Is it there?
C and for C, no, not for C. I'm saying for C it is 1, for E it is, and this is the correspondence, and for D it is 2.
Sir, like how can you explain? Like as we remove one word.
So once you see the in degree of A is 0 and the longest path is 0. So here is, it was C. So here is what? Once you remove that, what is the algorithm? Whatever the longest path is there, then plus add in that. So that's why the C of, if you see the longest for that, it will be 1, and the in degree will be removing 1. So it was previously in degree for C is 1, but once you remove that, it will become 0. Now for D, if you see that, so this is the longest path, and this is the degree, in degree. This is the longest path, this is the in degree. So in degree of C is 0. Once you remove this one, so the in degree of D will be updated. So once you remove this one, it will become in degree will be 0. Now the D have outgoing edges only, and the in degree what will be, whatever the longest, what is going to be longest path for D is, by this way we are coming. So this C have 1, and now 1 will be added, so it will be 2. That's why I just wrote 2. This is the way, like here, this is 1 and this is 2. Okay.
Yes.
This is the topology. Whatever the order you are doing, just update with the longest path also. Finally, this keep the whatever the, if you see that, finally if you remove what is going to be for F, I remove E and then C. I reaches to C and then D. And D, if you remove D, then finally E have in degree will be 0. Once you remove that, the D. So D in degree will be 0. And this E, okay, this E, D, sorry, this F will be in degree 0. So F will be degree. So previously it was 3, okay. So for F, the long 3, the order will be like this. And then once you remove this F, then the longest path will be here updated, which is going to be 4, and the order will be now G. So this is going to be topological sorting, and this is going to be the longest path.
For example, if we remove a vertex, we should add the longest path to the other vertices we are connected to.
Yeah, once we remove that, we'll add 1, and the degree will be subtracted 1. Or 1 means how many, once you removing that, the effective, like from there, the 1 degree will be removed.
Yes.
So the longest path in this graph is 4. And what is that path? The path is this one, and then this one, and then this one. This gives you the, what is the longest path? What is the, like this, how many edges involve that? And this order is give the how many edges involve that, and this is the topological sorting. Okay. And what is that path? Path is that you can, by this way in degrees, you can count like A to B, then E, then F, and then G. You can record that. Okay. So this is the longest path. Adjacency matrix is there to find the transitive. Okay. So transitive closure is, suppose if you have a graph, okay. Suppose this is A, B, C, D, and this is the graph you have. Okay. So transitive closure is of a graph is that what? You know, the suppose if you have this vertex, okay, and if the from this vertex to this vertex, if there is a path,
So your voice is actually not audible at all,
you
sir.
see that this is a path we have, this way and this way, this way. So in the whatever you have,
your voice
if
is
there
not
is a path, no. Am I audible? Am I audible now?
Sir, so now it's okay, but before it was actually stuttering very much. So can you please repeat this once?
Yeah, from here, no, transitive closure.
Yes, sir.
Okay. So suppose if you have a graph, this one, suppose this one, you have a graph, this one, and we want to find the transitive closure of this graph. So what is the transitive closure means? Suppose you have this graph, okay, and if you see that from A to D, we have a path, this one. Okay, we have a path A to D. So see that A to D don't have the edge, but there is a path to reach D. So what is the transitive closure means? You will, what you can do in that, the updated graph, whatever you will find in that graph, you will add the edges A, B, C, D, and this is C. So see that if you have, there is a path, then transitive closure of this graph. So transitive closure of a graph means it will be a graph which is updated one of the previous one. Oh, and what is the updation is that if two vertices have an path, then the updated, whatever I'm just writing here, in that you will, if there is a path, then you can add those vertices by a edge. So suppose here is, there is no edge between A and D, but we have a path. So transitive closure of this graph is exactly once you add these two. Now if you
Can
see
we
that
add a path between A and C?
A and C, so already, so yeah, there is a path between A and C, no? So this is the path A and C. So in the transitive updated, this will be, this edge will be updated here. This one. Now A to G also have, no, so there will be now there will be an edge you will add. Also similarly A to C have, right? A to C have path from this one and this one, so this will be added. Similarly A to D also have path, so this will be added. Now if you see that what is the updation is happening, we will try to add edges. We will try to, whatever the previous one, this one we have, we will try to add edges if you have, there is a path between two vertices. Now if anything is remain, from A to B have G to A have, okay, G to B have, G to C have, G to, okay, sorry, which one? B to D, yes. So see that B to D have we have a path. Okay, so what we can do, we can add a edge. Now is it complete? Is there any, if there any edge, but still I am not added, I have not added the sorry, there is a path, but I have not added the edge. So see that this is a kind of complete graph is happening, no? The for every vertices have the try to update in the edges. This is a kind of completion we are trying to do. So this is called a transitive closure of a graph. So see how the question could be asked, like how many edges could be added in the transitive closure of this graph? So the question will be like this. So how many edges we have added? This one, 1, 2, 3, 4, 5, 6. So 6 edges we have added to find the transitive closure of this graph. So this is called a transitive closure. But this is a, so this is a simple graph, that's why we are able to do. But how we will do in the form of algorithm? So what is that? So there is the importance of the adjacency matrix. So what is that? we know that this is an undirected graph, so we can find the adjacency matrix for this graph. Okay, we can find the adjacency matrix for this graph. And what is the transitive closure here? So see that how many vertices we have. This we have 4 and then 5. 5 vertices it have. So 5 vertices means we have, so there this is a matrix, adjacency matrix. So there is a matrix multiplication. So let me write that. Suppose now I am just writing a, okay, there are 2 vertex. Okay, suppose this is AB, and this is the one. Sorry, this is 0 and this is 1 and this is 1 and this is 0. So suppose this is a matrix we have, adjacency matrix of a graph. If you see that, it is only this graph will be, okay, this is the graph and this is the adjacency matrix of this corresponding graph. So we want to, if you want to find the transitive closure of this graph, it's already we have, no, there is, it is in the complete form. There is no, if you do the transitive closure, the same graph you will get. But suppose where I am, for the simplicity, I am just doing that. Suppose if you have graph, okay, so what you can do, you will find the adjacency matrix and how many vertex it have. Like suppose this one have the 5 vertices. So 5 times you will do the matrix multiplication of the adjacency matrix. Like once you will
Can
multiply
you please
here.
repeat from the beginning, sir? Like, how do we find the algorithm using adjacency matrix?
Algorithm means what is that I'm saying? I'm saying you will find the adjacency matrix of that. Okay. Okay. Once you find the adjacency matrix of that, suppose this is the adjacency matrix we have. Suppose A prime. Am I audible? My voice is clear?
Yes, sir.
Am I audible?
Yes, sir.
Okay. That's why I'm just stopped. Am I audible now? I just got the now I think. So suppose you have an adjacency matrix, this one. Okay. I'm saying let's say this is S. So what is that? You will multiply. What is S square? I'm saying means you will multiply the adjacency matrix this with the adjacency matrix the same. A square means S square you will find. You will multiply that. So what is that multiplication? No, so matrix multiplication is, suppose here is 0, 1 and 1, 0. So what is that matrix multiplication is? Here is 0, 1 and 1, 0. So what you can do, like you will take this row and multiply with this column. Okay, so this is going to be 0 plus into 0. And here is 1, it will be multiplied with 1 plus 1 into 1. Now take the same row and multiply with this column. So here is 0 times 1 plus this one multiplied with this one. So this is 1 times 0. Now what you can do, you can take the second row. Okay, the second row, it will be 1, 0 multiply with the first column, this one. So here is 1 time multiply with this 0 and this 0 multiply with here plus 0 times 1. And now here is again take this row and multiply with this column. So here is 1 times 1 and this 0 multiply with 0 plus 0 times 0. Now what is the process to add, or how we'll get this? So here is, there is one rule that if you multiply 0 into 0, you will get 0. 0 into 1, you will
So how do we choose a value
0.
of A to be as
1 into 0.
Sir, how
Sorry,
do
sorry.
we choose a value of A to be as 1, sir, in the adjacency matrix?
No. Could you repeat, please? What are you saying?
Adjacency matrix, how did we choose a value of A to be as 0, 1, sir? Because they have a niche between them.
Adjacency matrix we did right last time, how to find the adjacency matrix. If there is an edge, you will write there 1, otherwise you will write 0. That's the way, right?
Yes.
So that's why I'm doing nothing more. I hope I am just expecting that you know how to find the adjacency matrix. I am not going to discuss that is also because last time we did, and that is the previous week thing. And writing the adjacency matrix is not a very big problem. If there is an edge, you will write there 1. If there is no edge, you will write 0 there. That's all. And what is that? If you just need to write A, B, C, D, G, this A, B, C, D, G, A, B, C, D, G. And what is that? If there is an edge between, from here we'll start, like if there is an edge between A and C, so here is A, this row is A, and this is column. So A and C, this says there is an edge, then A and C will be, there will be 1. And suppose there is no edge between A and B, so there will be 0. So this is the process to fill the adjacency matrix, okay, to find the adjacency matrix of a graph. I'm just here explaining how once you will multiply then multiplication, how the multiplication will be here. So 0 times 0 will be 0, 0 times 1 will be 1, 1 times 0 will be 1, sorry, 0. And 1 into 1 will be 1. So this is in the multiplication case for the ones. Then this is the different multiplication. Okay, it's look like the same multiplication, but this is not the same multiplication. This is called the binary multiplication kind of thing. And the another thing, add 0, 1, 0, 1 will be 0, and here is 1 plus 1 will be case, and this is the multiplication in the binary case. So finally, here what it will be? Here it will be. Can you tell me what it will be here? This will be 1. What is going to be this one?
0, 1.
Yeah. Am I audible right now clearly?
Yes.
Yes.
Okay.
But in the middle, it gets
Yeah,
stuck.
in middle, yeah. Yeah, I usually get the message. Here is just message pop out that my internet is unstable. That's why I usually stop here. So now here it will be 0 plus, here will be 0 plus 0, it will be 0. Here is what? Is 0, 0, here will be 0, and here is 1 and 0, it will be 1. So finally the matrix multiplication you will do, you will get here 1, 0, 0, 1. So this is the, if you suppose this is a, you know, adjacency matrix of any graph. Suppose this is M, for example, I took multiplied, and this was, suppose this is A, no? So once I multiplied, here we got A square is actually this graph, this adjacency matrix. And you can find from the adjacency matrix, you can find the graph also. So what is that? Transitive closure in the terms of matrix multiplication is how many vertices you have, that many times you have to multiply. Like suppose for this is S is the adjacency matrix of this graph. Okay, so what you will do, you have to find S0, which is exactly S, and then S1, which is, sorry, it is not S0.
Sir,
Okay.
the entry in the adjacency matrix will be 1 only if there's a connection, right?
So here will be means you have to find S1, which is exactly S, and S squared means you have to multiply S into S, S cube. Okay, S into S into S, you have to multiply 3 times. You can multiply easily that. First multiply 2 matrices and then multiply the third one with the same thing. Similarly, you have to find S4, S5. So it have 5 vertex. So how many times you have to multiply? You have to multiply 4 times. Means you have to find S4. Now finally what you will do, the adjacency matrix of the transitive closure is going to be, which is generally denoted as A plus. This is called the adjacency matrix of the transitive closure, means which we got this one. You can write this graph as in the form of adjacency matrix. So this matrix, whatever you got finally from the directly from this graph to this here, this could be, this adjacency matrix can be get from once you add S1, S square plus S2 plus S4. So whatever you got this one, this is going to be your adjacency matrix via this way also. So this is an algorithm to find the adjacency matrix of the transitive closure. Okay. Now Dijkstra we just now discussed, that is in starting the Dijkstra algorithm, that is exactly for the Dijkstra algorithm is work for the non-negative edges. And what is that the Dijkstra algorithm? Dijkstra algorithm is used for to find the shortest path in the graph from a single source vertex. You want to find the shortest from a particular vertex. That means suppose if you have a graph, okay, suppose you have a graph. So from here, the Dijkstra algorithm says from this vertex to, suppose I want to find the shortest path to this vertex. Okay. So by which route I will go with the respect of weight. Suppose the weight is also given. So with respect to weight, how I will proceed to reach this graph. Suppose this is A and this is G. So how I will proceed this graph G so that or even from A to from all, or even I want to find to this graph this vertex Z. So by which route with respect to weight so that I am reaching the weight will be minimum. By which route I will go so that the weight will be minimum. Then the weight could be anything. Weight means here, suppose here from this city to this city, the transport price, you can transport cost, you can say, suppose this much cost is there. Then here from this city to this city, this much cost is there. So what is the shortest path I will choose so that I can reach to this vertex G or this city G with the minimum cost? That is called that is in the terms of, you can see the finding the shortest path in the terms of minimum vertex.
So what is this topic
So
which
minimum,
we just discussed?
sorry?
So which is the topic name which we just discussed? So what is the topic name which we just discussed?
That is the Dijkstra algorithm, no?
Yes. So because I have not yet watched the lectures or so much.
Sorry.
Yes, sir.
The Dijkstra algorithm is why I'm very quickly I'm discussing, because in the starting there is one question one person have asked, and that asking how we'll find the that flooded thing. No, in starting I just discussed. That's why I'm very quickly, and that is not the purpose, because the Dijkstra algorithm is exactly to find the, if you see whatever sir is discussing in there, that is the only algorithm to finding the minimum way to burning point. Burning cities are there, but important you can, so the second important, when the weight is negative, then you cannot do with the Dijkstra algorithm. There is another algorithm, you can Bellman-Ford algorithm. Once the edges is negative in a graph and the graph does not contain any cycle with the negative edge, okay, negative weight, then you can able to use the Bellman-Ford algorithm. So
here, can you just explain what is negative weight or positive weight, sir?
Negative cost means, negative weight means, suppose if you have a graph, okay, suppose this is the vertex you have. So the weight is here is 1. Let's say here is for this vertex is, let's say this is the -1. Okay, and this is 1. This is 2. So for this graph, okay, for this graph, the negative weight is here is what? -1. Here is the negative weight between the edge, this one, between that edge BD. This edge have the negative weight. And suppose I am making like this. Suppose here is, let's say this is 2.
Sir,
okay,
but
or let's say this.
Sir, but while finding the shortest path using Dijkstra algorithm, if it's the negative weight, how do we do it, sir?
So if it is the negative weight, then you cannot use the Dijkstra algorithm. If there is a negative weight, okay, if it is there is a negative weight, then you cannot use the Dijkstra algorithm. Then you will use the Bellman-Ford algorithm. What is the Bellman-Ford algorithm is? There is a way to find that. We will try here. I will going to discuss that. What is that algorithm. So Bellman-Ford algorithm is to find the shortest from a particular vertex to for all. This is the called the single source. Suppose from this vertex to, with respect to whatever the age is given, no, with respect to this, whatever the vertex is given, no, with respect to this from A to for all vertices, what is going to be the shortest path. So this is called single source shortest path, means from this vertex, this is source vertex, you can say, from this vertex to all vertex, which is going to be the minimum or shortest path, which is going to be the shortest path. Okay. And if there is a negative weight is happening, you are allowing the negative weight in the graph, then be sure that there should be no cycle. Suppose here is what is happening here. If you see that, suppose this is the graph you have, and this is the direction is
So this
given.
one is for which algorithm you are trying to explain, sir? Is it Dexter algorithm or
God.
Bellman-Ford?
Bellman-Ford, I am explaining here below. After that, this is explaining. So
Yes.
only for you this is confusion, or for all of you I'm just explaining? And
Sir, no, sir.
sir.
Actually, because I haven't watched the exercises. I had my college also. This is the first lecture I'm even attending for week 11. So I've not seen anything. So that's the reason.
Okay. So whatever I am saying for others, is it clear what I am saying? Or if it is problem, then I will slowly say, and very slowly, and again one by one categorized form I will tell. Whatever I am
Sorry.
discussing, is it clear?
Yes, sir. Yes, sir.
Okay. Okay. So what is happening here? If there is a cycle, suppose see that this is a cycle is happening, and with the negative weight cycle, what is happening? The weight count, if you see that from the vertex A, if you say in this direction, if you go, the weight is 1, and then this weight is also assume, you can assume this weight is 2 and this weight is 1. So if you go with like this, and then this is -3, so minus or 1 and -3, and then if you say that again it reaches A, which is 1 weight, so finally it have -1 weight. So see that there is a cycle is happening, but the negative weight, see that this is have the negative weight. So this is not, this should not happen in the graph. Once we'll try to use the Bellman-Ford. If there is a if there is a negative weight or negative cycle is happening, then this Bellman-Ford algorithm will not work. So what is the Bellman-Ford algorithm? Let me write that. What is exactly? From the single source vertex. So I want to find the from this vertex to all vertex, what is going to the minimum shortest path? What is going to be the shortest from A to either B or C or D or E, which is going to the minimum path or minimum, yeah. Okay, single source. So what is the process?
If you can increase the weights, then it will be more precise, I think.
Sorry?
If you will increase the weight, then I think it will be more precise, because all are 1, 1, 1, 1 and -1.
So let me take an example from the even in the activity itself. So this is the single source shortest path with the negative
Question
weight.
which I asked about the Dijkstra, you can take that question itself also.
Yes, sir. 11.6. Yeah. This one.
From here, we can take this one even. Let's discuss this one.
Yes, sir.
So suppose this is the graph we have. So see that in this graph, I want to find the single shortest path from 0. From 0, it could be from any vertex you can choose. I'm just trying to do with the 0 vertex. Either you can choose 1, 2, or any vertex to all vertex. From 0, from this vertex to all vertex, what is going to be the shortest path? And the path is with respect to the weight. So what is that algorithm? The algorithm is, you will write in this fashion. What is that? D and 0 you can write, that V is you can 0. That here is the single, that vertex from source vertex is here you can write. And here is vertices is 0. And here is 1, 2, 3, 4, 5, 6, 7 you have. And how many times the iteration will go? The iteration will be exactly how many vertices it have. It have the 7 vertices. So 6 times this iteration will go. I will tell you what is the process to write that out. So 6 times means here is this one. This is one iteration. 1, 2, 3, 4, 5. And 6. Now I'm suggesting you please watch the lecture. Without that, it will be difficult to understand that what is I'm discussing here. Once you watch the lecture, then easily you can find what is that algorithm.
Sir, at the end,
Here is,
can you just, sorry, sir, can you just briefly not explain, sir, all the algorithms in which case it does not apply? Can you just
sorry.
At the end, can you just still mention all the algorithms and in which case the algorithm does not apply?
Okay, sure. So here is the 6 time. Here is the 7 vertices. We have the 6 time iteration. 6 iteration we'll do. Okay, this is 1, 2, 3, 4, 5, 6, 7. I just wrote here. It's not needed. Okay. So what is that? In starting, you can assume that the shortest path or weight, here is the weight will be written. So shortest from 0 to all vertices, assume that all have, except the 0, you can assume 0 or infinite. What is the, I think it sir have wrote infinite. And in the starting, you can assume the shortest path is all infinite. This sign is given. You can give any sign in the fashion of, or you can, that is the purpose of why this infinite sign is there, means you are unable to find the exact weight. Okay, so that's why. My voice is clear?
Now
Yes,
clear.
sir.
Am I audible right?
Yes,
Yes,
sir.
sir. Yes, sir.
So in starting you can give the infinite to all, or let me once
No,
for
zero
0 from
and
where it is
zero.
started. 0 will be
Sir.
0,
So,
no?
yeah.
For 0 it is for 0 because the reason is we know, that infinite is, the reason is why there will be no infinite is because we know that the shortest path is 0. From 0 to 0, the shortest path is 0. And with respect to all other vertices, we don't know what is the weight exactly. That's why the infinite sign is there. Okay. Now, what is the process? The next iteration means here is start moving. Okay, from 0 to 7, if we reaches, then what will be here? Then 0 to 7. So 0 to 7, there will be a update which is 6th. Here it will be 6. And
10.
0 to 1, it will be 10.
10.
And rest all we don't know. Till now we have one iteration we know. This is the process we are doing. So and
0 to
rest
4
will
also?
still it will infinite. Okay, here will be 0, again 0 for 0. And which is from 7 to 0, which is 4. Okay.
Sir,
Now
four,
from
sir,
sorry.
0 to 4 will be 4. Arrow is going from 0
Here
to
is 0 to 4 is there. Now from 0, okay, from 0 to now from 7, let's start from 7. 7 is here is going to 6. So from now you can see from 0 to 6 is the what is going to be the shortest path. You can see it here. How much?
4.
6
4.
minus 2, which is 4. So 0 to 6. So 6 will be updated here. So from infinity it will be 4 here. Now it's changed. Okay, now from 7 any other, there is no outgoing edge. Now from 1 it is 1, from 2 here is 2, so here will be what, 11. So 0 to 1 the edge will be 11, sorry, weight will be 11. So 0 to 2 is here, so weight will be 11. And 4 is remain, so there is no outgoing edge for 4, so no need to check here for 4. Now rest all will be the same, so here will be the same 4, and rest all the whatever whatever the still I'm not doing anything update, the same will be continue. So here will be 0 infinite. Now in the next step we reaches 6. So from 6, so outgoing edge is 3. So here is from 0 to finally, if you add that, what is going, we are getting 8. So from 0 to 3 we are reaching with the weight 8. So here 8 will be updated. Okay. Now from outgoing edge from 6 is there, nothing. And from 2 we have outgoing edges. Yes, from 2 we will reach 5 and 7. So now 7, from 7, see that we are also reaching 7. So this we have 10 and this is 1. This is become 11. Now from 2 we are reaching 7, which is with the negative weight. So 10 and minus 3, it will become 3 by this way. And then this is 3 become. So see that now we have to, here is 6 will be exactly 6. Now we have to update here from 6 to minimum, which is 3. This is the updation. So this is the Belmont fold. You have to update one by one once you are doing the algorithm. Okay, we are proceeding with the iteration. You have to update that. So see that previously it was 6, but now it is updated once we start moving from 0 to 2, from 0 to 1, then 2, and then 7. Okay. Now from 2, how 5 is also given. So 5 is, what is the weight, is going to be 10, 11, and then it is minus 10. So which is going to be 5 to 11, which is 1 is here, and then 2 is any other place, no. Okay, so finally, and rest all here will be 4
How
same.
2 and in the third row and second column be infinity?
This one, this 2, or this one, they here.
No, sir, the in the adjacency and the matrix 0, 1, 2, the 2 and the second column.
This one, 0, 1, 2 here, and this one.
Yes, sir.
From here to here. From here to here we reaches, no?
Here cursor is not
See-
visible.
Okay, from this one to this one, is that? So from here to here, it was previously, no? Before reaching to 1, this is one step we did. From here to here, this is the 2. So this is the 2 is given. So this is the weight, 10 and then 1. That's why this update is there, 11. Okay.
Yes, sir.
Okay. Now here will be 11 same. Here is infinity. Here is the 10. No, previously it went in, how it infinity. Here will be the 10 will be continue, and here 0 will be continue, and here the 4 will be continue. And now infinity is removed. Now here some number is given. I have updated 7 from 6 to 3. Now we reaches here. Okay. Now from 5, outgoing edge is to 6, and this is 4. So what is that going to be here is 10, or from 5 to 6, how much? This, if you reaches to 6 from this 5 to 6, how much it will be?
2, sir.
By this way, and this way. So how much it will be? 2. So 6, see that 6 is the vertex is here. It was previously 4, but now it will be 2, right? By this way, if you go. This one, by this way, and this way. Correct?
Yes, sir.
And if you go 4, this way, by this way, and this way, and then this way, what is going to be weight for 4 now? 6, right?
6, yeah.
So for 4, 6, but here is 4 is given. So no updation will be, it will be continue with the same, because 6 is greater than 4. Now what is remain? From 5 is done, and what is we did here? 6 is there, no? 6 we reaches, no. Okay, 6 and 3, from 3 still remains. So from 3, yeah. So from 6 to 3 we reaches, that's why it is become 3. If you see that, this is 8 is there. So 3 is still remain to update. So 8 is from 3, there is outgoing is 2, and this is 4. So if we go by this way, 0, oh sorry, 6 is, what is the weight of 6? What is the weight of 6? Which is 2. And okay, so 6 weight is 2, and then here is 3, and from 3 to 4, if you go to 4,
Sir,
then
actually, a
what is
person is not visible.
okay. Okay. I think, is it happening for all of you or only for you? My cursor is visible to all of you, right?
No, sir, actually not visible, sir.
Okay. Okay. So I am making here the line. So from 0, okay, to 1, I just went to 2, and then here is, no, how I went to here it will come for 6, it will come 2. So here is, we, by this way we went, this one, and then this one, sorry, this one, and then this one, it's, and then this one, for 6 it will come 2. And now from 2 we went 3. So what, how much it will become? For 3 the weight will be what? 6 minus 8 is there. Oh, I just wrongly wrote here, no? This one.
Actually, what can you please tell what are you explaining now, sir?
Sorry.
Sir, could you please tell which topic you're explaining now? I'm facing a problem because I haven't watched the lectures. So, like, if you could, is it possible if you can explain in detail,
I'm
sir?
explaining Belmont-Ford algorithm. Once you watch the lecture, then it will be very much clear to you. Otherwise, if you don't watch, then it will nothing will get.
Okay, so because I'm not able to understand most of the things which you're discussing. So,
yeah, the reason is you haven't seen the lecture, no? If you have gone through the lecture, then you will. Because if you one by one you start discussing, then it will be difficult.
Your voice is cracking.
Once you, that's why this, at least for graph 3, have to one. Now is it clear? Is it better?
Yes, sir.
Okay.
So
for 6 here, for 6, once we reaches the weight is, here is 2 we got. Okay. 6, sorry, by this way we went from 5. So from 5 is this one, then this one. Okay. So okay.
Sir, from 3, there is no way to 5.
By which way we reaches 6 here? So that weight we got to 0 to 1, and then 0 to 10, and by this way. Okay, by this way we went here. This one, then this one, and then this one. So that's why the weight become of 6 is 2, because this 2. 10, yes. That is 2, and from 2 to 3 we moved. So what is the weight of 3 now? We got 6. So yeah. Weight of 3 is 6 now will be happen here. So here will be 6. Okay. And then okay, then weight will be from 6 to, it will be this one, and this 2 is 11. So 2 will be 11 continue here, because there is no so from 3 to 20 will go, still the weight will be increased form. So it's still the 11 will be continue. Okay. Now for 1, the 10 will be exactly the same. Here will be 0. And here is for 5. For 5 is, by this way we went. So the weight is
Like
minimum.
the Bell-Manford algorithm in detail, sir.
Sorry.
Can
Sorry?
you explain the Bell-Manford algorithm in detail, sir, and whatever you're doing now in detail, if possible?
See, that for that you have to lecture only, because if I will start explaining, so whatever I am doing here, that is the way I am doing. No, if you are not getting this sign, what is the infinite here, then you at least you have to once you have to see the lecture, because without
Okay, sir.
then it will be very difficult for me to cover.
Okay, sir.
In this way only, the lecture also in the same way only, sir. In the same way.
Sorry.
And lecture
Sorry?
also explaining in the same way only, sir.
Yeah, in the lecture, if you say that the same is, that's why he's missing the part is reason because he didn't watch the lecture. No, so if you once you watch
Okay,
the
sir.
lecture,
Sorry,
you
sir. I
get it.
think I guess, sir, I'm just disturbing the text.
And the seven is the same. The weight is will be continue. So here is the weight. Okay. So 7 for 7, if you see that the weight for 2 is 2. Okay. So 7 is the same. The reaching is the 7. The incoming edge for 7 is only by this way, and this way. Okay. So 7 will be continue. Now one updation is still remain to do that, because we 1, 2, 3, 4, 5, and the 6th time we have to do. Okay. Now from again 0 to 10, this will be continue. 2 will be the same because there is no update is happening. For 3, so for 3, so here is 3. So any other way we are going to reach 3? So there only this way. For incoming edges for 3 is only this way the same. So the same will be continuing here. 6 and 4. 4 is here. So 4 is by this way we can come to 4. So the weight for till reaching 3 is 6. Okay. Weight for reaching 3 is 6. And now to reach 4 is this way. So that means here is the negative weight. So what is going to the weight for finally? 4 is 6. It will reduce. So how much it will be? 3. So 3 is lesser than 4. So here is the update will happen for 4. Now for 5 is the same process, because here is 2 and there is no okay, there is 1 to 5 reaching the 5 is the only this way. You see that the only the
Just
same.
no, sorry, sir. This way, 3. How we got a 3, sir? 4, 4. If
For
it's
4
6,
is 3. 6 is there. To reach 6 is the weight is 6. For reach 3, the weight is 6 we got.
okay.
And what is the root? This one, this one, this one, this one, and then this one.
Okay, sir.
After
Okay.
3, then reaching to 4 is that's why here negative weight. That's why it reduced. Now for 5 is the only coming way is this one. So that's why there is no update will be in that. For 6, the same, there is incoming is the previous one. That's why in that there is no update in that. And for 7 is the same previous one. So this is going to be the same 3 is here. So this is going to be your final updated shortest path with respect to weight from 0 to all other vertex. So that means finally what is going to be the weight to reach here 6 is the shortest path is 2, for example. Now for 4 is the shortest path is from 0 to 4. To reach the shortest path is going to be 3. Now if you see that here, what is the, where is that activity? Now let's match with the answer. So this is from 0, it is already given. So D5. Okay, so this is D4. So this distance is the shortest passage. So D5 is what? How much we got? D5 and D6 is
we got 1. D5 we got 1.
So D5 and D6. So D5 is 1, but D6 is 2. So this option is not going to true. D3 says 5. So D3 is 5. D3 is 5. So this is that option is also not true. Okay. And D4 is 2, it says. So D4 is, what is D4 is 3 we have. Okay. I think we are missing. So D4 is 5, it says. So here is D4 is 5. We don't have. So which option is actually correct? Let me check that. I think I made a mistake.
First one, sir.
The first one, no? So D6 is saying 1, but D6 what we got? D6 is we got 2. Okay, so I think I made a mistake here. Let's check here. 0, 11, and this is 1. Oh, this is 2 no we are getting. So any
Yes.
other way to reach here? Okay, this way 10 to reach 6 is only 2 ways, either by this way or this way we have. So if you are reaching by this way, okay, this way, then this way,
Sir,
and this,
that way. No. The 10
2
to
to 7,
7,
sir.
6.
10 to which is here is going to be, okay, this way. Okay,
No,
sorry.
10,
This
0, 1, 2,
sorry,
7, 6.
0.
One.
No,
Okay,
1,
where is
2, 7, 6.
0, 1? Okay, 0, 1.
1.
Zero.
Right side, sir.
Okay,
2,
by this
7.
way and this way.
Yes.
Okay, this is 11, this is -2. Okay, so that is the update we missed, I think then. So previously 6 have 4, no? Okay, so we for 7, when we are doing for 7, we didn't update it, no? So this way is 6 actually. So that's why it is going to be 1. So once we by this way we reaches from 2 and then 7, I need to update here. This is going to be 1. So yeah, the 5 and 6 we have the same weight, which is 1. So we missed that. Otherwise, this is the process. This is the Bellman-Ford update is there. Okay.
Correct me if I am wrong.
Okay.
Sir, except the negative values, if we take all the positive values also, then also Bellman-Ford will work like this only?
Yes. Negative numbers is also kind of, you can write like this, right? Also plus of minus that. You can think, so we still, sorry, positive number is also can we think like this, minus of that.
And so the main difference or the key difference between
still the
this
Bellman
and this and the previous algorithm was that there we were fixing the values which was the minimum, and here we are not doing like that.
Yes, here we are doing the updation, and also that is previous one is the Dijkstra is for the only positive
Positive values,
but here is the Bellman is negative also.
Okay, sir.
And now the next algorithm is the Floyd-Warshel algorithm. This is for the all to all. So I am just skipping this because of this video only. I am suggesting you, if you want, say once you watch this video, no, everything will be clear to you. Once you watch this, because this once I will start, no, it will take very much time. It will take 1 hour or more than that. So once you watch this lecture, everything will be clear how the algorithm works. So this is here is the Bellman have discussed in a very slow process, and everything have discussed. Even you can watch that. So from here you can see that have discussed. That's why I'm not going to discuss. Otherwise, if you have doubt, we can solve the problem related that. But once you watch this one, this problem will not be a big issue. Okay.
But
Here is it will actually take longer time because there are so many steps we have. I have to take at least one directed or directed graph. I have to take a proper graph. I should need it, and each time I have to do. So if you see this video in this lesson, everything is very clearly explained. Once you watch that, if you have doubt related that, you can ask me. Okay.
Hello,
now,
sir.
Yes. Hi.
Sir, actually, I just joined this meeting. So I have a doubt in activity question, activity number 11.5. So can I ask this, or you will do that later?
Yeah. So just now we discussed so we can discuss that 11.5 is for the.
Yes, last one question. It's just a little doubt, sir. I don't know how to go for that question.
This one, the last one. At what time will be the city? So
That
same
9
it
minutes.
is for the. Sorry.
Yes, sir.
It's 9 minutes, sir. You can add the shortest route, then you will get a 9 minutes.
At what time will be all the cities will be flooded?
Yes, sir.
So we need to find the maximum, right? Maximum time is that
No, sir,
with the
minimum.
sort,
I think.
sorry,
Minimum
minimum.
time, single source
Minimum
shortest.
time.
Yeah, this is the single source. So at what time the all cities will be up? Minimum. Minimum
Yes, sir.
means here is one by one. What is that? You can see. Let me take that root. Let me put the root also.
So just
The
to do
timing
the
also.
solution briefly, sir. Actually, I don't get the answer, sir. Maybe I'll
So
do
what is
it
that?
at some
Yeah, this
point.
is the exactly on the Dijkstra. So here is what is the Dijkstra is the same. I will do. So here is the flood, and this one is flooded now. Okay. So by this
B to
way,
C.
Yes, sir.
water will start coming this way. Okay. So within 1 minute. So within 1 minute, C will be flooded. So within 1 minute, C will be flooded. Now from here to by this way, if you go, so if you coming by this way, it will take 4 minutes, but by this way, if you go, it will 3 minutes. So within 3 minutes or after exactly after 3 minutes, the city A will be flooded. Now if we go here from so
sir.
after 4 minutes, it's already flooded. Now if you start moving this way, this way, this way, 3 ways are there. So after 1 minute, this city will be flooded. Okay. So here is how much time it took. This took 4 minutes. And by this way, here is it took 10 minutes. Okay. So it will take 10 minutes, and by this way, this will flooded with after just 4 minutes again. This in the 4 minutes, it will also flooded. And if the water is started from this way, it still take 14 minutes. But by this way, if we by this way, it will go this one and then this one. Okay, sorry. So this took 4 minutes.
Then
So
to G,
yeah,
sir.
this took 4 minutes. Then it will start this way and this way. So it is already flooded. It's already in this way. It's moved. So how much it now take this way and this way? It will become 8.
8
Yes.
G.
Back to
And
E.
now still
one
this
more
water is coming. This water is still coming. Within 8 minutes, it's flooded. And this still water is took 15 minutes. So this is done. Now by this way, again, this starts. So already it doesn't matter here. So this vertex is started moving. So this means after 9 minutes, it will be flooded. So after 9 minutes, it will be flooded. Here is, it took 10 minutes to reach from this 3 to 10. So here is 10 minutes and here is 9 minutes. So
Okay,
see
sir.
that
Thank
it
you,
is
sir.
in the 9 minutes, it is flooded. So see that after this is the minimum time, which is the last one, which took the time. Otherwise, all have flooded.
Thank you,
Okay.
sir. Sir, I got it.
So by this way, this is also the Dijkstra is says. This is the actually algorithm. Whatever I am doing here, this is the Dijkstra algorithm. You have to go with the graph. There is no matrix forming like this, or there's nothing. This is the way only. This is the Dijkstra algorithm I discussed with an example.
But sir,
Now the next
11.6, no, 11.6, the first question we discussed so far is, how is the other two answers, sir? D of 4 is some options.
Okay.
D of 4
Where is
and
that?
D of 3 and D of 4 also correct. How it will be?
Where is that? This one is also correct.
Yeah, D of 4.
Okay, let me check how many options are correct we have. Okay, so D4 is, you have here is 2, and what D4 is we have D4 is 3 we have. So actually we made a mistake. No, here is okay. So here is for 6, what is that? 1 we have. For 6 we have 1, and from this way we can go and then this way. So for 6, 3 will be what? 5, right? What is going to be the weight for 3? 5. But what we have the weight
5.
for 3? See that that's the wrongness here. So it will be 5. And from 5 to again this way, what is going to be 4? That's why because of this mistake it is happening. I didn't update it for 6. From 6 to this one and then 4. What is going to be? This is 5 and then this is 4. This is minus 3 is there. So for 4, what it will be? 2.
Okay, sir.
So there is a mistake happening because of this 6. I didn't check after the 6, and this is the mistake happened. But this is the way to update and to write that. If you are going with the correct way, you can choose that. Okay. Now the next is minimum cost spanning tree. What is the minimum cost spanning trees? Let me take an example.
Excuse me, sir.
Yes.
Sir, in this, sir, the diagram that you were just showing right now, sir, how that 8 value came, sir? Can you please explain, sir?
This one.
No, sir, the diagram that, yes, sir, this one, sir.
For 8 value, for 8.
Sir, below 1, sir.
This one, 8. How
yeah.
8 come? This one.
Yes,
So
sir.
by
yes,
this
sir.
way, no? By this way, this route. If you take this route, this one, and then this one, and then this one, and then this one. So this is 1, this is 2.
Okay, sir. Okay.
3, and this is 1, 4, and then 8.
Yes, sir. Yes, sir. Thank you, sir.
Okay, so next is the what is the minimum cost spanning trees? The first thing is, what is the spanning tree? The spanning tree means we want a tree, or it is a tree where all vertices is connected, and there should be no cycle. Tree is what? Tree is means there should be no cycle. And spanning tree means it will span the whole graph. Means, let me take this one for example. Okay. Here is if you see that here we have a graph, this one, no? So spanning tree means, what is the spanning tree? First, what is the tree? Tree is a graph which does not contain any cycle. This is the definition of the graph. Is tree is nothing but a graph, but here is it will not contain any cycle. Is this a tree? This is not a tree reason, because it contains a cycle. So see that this is on cycle. The direction is not given, but you can think that this is a cycle, right? Why the cycle is happening? Because any way you can go. This is not direction is given. So this cycle is happening here. So can we get a tree? So can we get a tree here? So if you update, or means here is, see that what is happening. I am writing a tree with from this graph is, okay, this one, or by this way, this one, and this one, and this, and this. So see, this is a tree, or this one, and this one, and this one. So see that this is a tree. See, whatever I just wrote here, there is no cycle is happening.
Yes,
there is
sir.
no cycle is happening, and this is a tree. So that's why it is a tree. Now the spanning tree means it will, like, whatever the vertices you have, no, if you start connecting, it will exactly, you can find the whole graph. So how it is, you can connect like this, and then connect like this, then it will become your graph. So this is the mean of spanning tree. So whatever the tree we have, no, from that tree we can generate the whole graph. So this is the mean of spanning tree. So minimum cost spanning tree means the weight, suppose for this one, let's say the weight is 2, 3, 5, 7, 9, 10, or let's say here is 1 or minus negative, you can give also. It doesn't matter. I think in Prism and Kruskal have both we can apply. So here we can going to discuss that also. So what is that algorithm? Suppose this is 2 here, this is 1 here, okay, and this is the weight is here is again 1, you can think. Okay. Now what is that? We are trying to find a tree which have the minimum cost. There are many trees, right? This is one tree, or see, whatever I just wrote the previous one, like this, and then this, and then this, then this, and this, and this. This is one tree related to this graph. You can write the different tree also. What is that? This one,
So
this
which
one.
question is this?
This is of the activity we are discussing under the 8th lecture of week 11, minimum cost spanning tree. And this is the, I think, this is second question, or this is the, I took the graph here from graph and I am discussing. So this is another tree. This is another tree. Okay. This is this one. Okay. This we have, and this is, then this is, and this is. So see that with respect to this graph, we have another tree. So this is a tree also. This is a tree also. Even the spanning tree. So this, if you connect this way and this way, this will become a spanning tree. So we have two spanning tree, this one and this one. But can we get a tree which have the minimum cost? Like if you count the cost again, if you write this, what is going to be the weight here? So this is 2, 5, and this is 2, 1. Okay, and this is 2, and this is 1. If you count the cost here, so what is the cost is just need to add the weight. Count the weight. Here is 2, 5, 7, and this is 8. Okay, this is 2, 5, 7. This is 9, and this is 10, and this is 12, and this is 13. So cost or weight of this spanning tree is 13. Let's count for this one. So here is 2, 3, and this is 2. This weight is 2, and this weight is 1, and this is 2 here. This is 1. So count this weight is 2, 3, 5, 5, 6, 6 to 8, 8 to 10, and 11. So see that the weight of this spanning tree is 11. So there are in many ways, there are many trees we can find which have weight, different weight. But we want to find that spanning tree which have the minimum weight. There could be another tree also which have the weight lesser than 11 also. We don't know, but we can. But what is that weight? What is the weight of that spanning tree? We want that. So this is the problem for the minimum cost spanning tree. This is the minimum cost spanning tree. So how we can find? So
did you perform the Prim's algorithm? Yeah.
So to find, we have two algorithms, which one is the Prisma algorithm and another is Kruskal algorithm. So what is the Prisma algorithm? So Prisma algorithm says so in a spanning tree, the all vertices will be given. Okay, all vertices will be given. So Prisma algorithm says take that vertex which have the minimum weight, or take two vertices which have the minimum weight. So suppose here we can take this one and this one. So which have the minimum weight. So this one and this one. We took 3 and 4. Okay. We took 3 and 4. Just a minute.
So now you're speaking something.
Yeah. So we have this one and this one. Okay. This is the one weight. Now from here, from this vertex which have the minimum vertex, from this vertex which have the minimum weight, by this way if you go, so which have minimum. So from this vertex which have the minimum.
Cursor is not visible since.
Okay, but is it happening for all of you? Is this happening for all of you? My cursor is not visible. I'm writing like this or any.
Yeah. It is visible.
Sir, if you are just pointing
Maybe somebody have.
Pointing it out, it's not visible, sir.
So this time is visible, no? Because of some internet issue may possible. Okay, so that's why I will draw the graph. So from this vertex, and I choose the minimum weight h. Okay, I choose the minimum weight h, which is this one, with the connected vertices is this one. So I choose this one and this one, and which is a minimum now this one, which is connected with this whatever we got the previous one. So connected with this one is this weight. So I choose this one. Now connected with this one is 2, and by this one is 1. So write that also. I chooses this one.
Okay, sir.
So this is the way. Now, from this
Sir,
4
the
vertices,
pointer is not at all visible. So your writing is visible, but not your pointer when you're pointing it out. So it's very difficult to follow.
is it happening for all of you? First question is it happening for all of you? Sorry?
Yes, sir. Yes. Yes, sir.
It is not.
Whatever you are writing, that is visible, sir. Pointer is that cursor is not visible.
Like when you're trying to
Okay.
show that it's from 1 to 2, we're not able to see which diagram we're trying to
While
show.
explaining, it is quite confusing.
Oh, sorry. Then just a minute. Oh, I can change my cursor. Okay, but how it could be? Like for me, it is visible, and this is the live recording, and it is just going. Is it visible?
Whatever you are doing with the
cursor-
pen, that is visible, but the pointer is not visible.
Okay.
But you can dictate because the edges are labeled. You can dictate as well.
Yes, sir.
Okay. I don't know how I can change the different format, annotate.
This is and edges are labeled, so you can go, I think.
Okay. Okay, I will try to write here. Okay, so here is I'm into here, this one I'm saying. So from this vertex, so whatever we have, this one or this one or this one or this one, from these 4 vertices, whatever the connected edges which have minimum weight, we will try to get that, and such that it will not make a cycle. So see that for this one and this one, okay, these two have the, if you connect with other 4, have the minimum weight, this one. But if you add this edge, it make a cycle. So that's why we are not going to add this one. Okay. Now we have to check for others. For this vertex, the minimum weight is which one? This edge. This edge we have. So that's why this edge we can write. Now this is new vertex we have. Now again, from this vertex, this edge there is there 5, and for this vertex, this edge is there. So which we can write? So minimum one will choose. So this one is will choose. So here is 3. Now from this vertex and this vertex we have. So again, this is 5 and this is 1 we have. This is 2 we have. So we will choose simply this one with related to this one. This is going to be the corresponding edge. Now see that this is a spanning tree. Now, if you check that, this will span the whole graph. And also, now let's count the weight here. So this is 2 we got, 3, this is 5, and this is 7, and this is 8, and this is 9. Okay, and this is 10. So the minimum cost spanning tree for this graph is by the Prism algorithm is 10. This is the way. This is the algorithm to find this is the Prism algorithm. You will write those all vertices, or sorry, edges with the connecting, whatever in starting you have to choose the minimum edge, either you can choose this one, or anyone which have the minimum edge, and then choose those edges which is connected to these two vertices. So like this one, and then I chooses this one. And then once we choose this one, choose those edges which is connected we have with the whatever we have vertices. So once I choose this one, it's make an cycle. So that's why we are not going to choose this one. Now with the other vertices, we will try to check like as here we did. So by this way, and finally we just this is the spanning tree we got. Okay. Again, let me erase the whole here. Okay. Now what is the Kruskal algorithm? Oh, this is I erased. This is 2, 1. Oh, sorry. Let me back to with the weight. This is the weight. This is so this is the weight we have. So see that by the Kruskal algorithm, we can get the different spanning tree, but weight will be same. Okay, so whatever the way you will get the weight spanning minimum cost spanning tree, or whatever the weight you will get of the spanning tree by the Kruskal or by the prism, the weight will be same. Yeah, the structure or the tree will be different. So what is the Kruskal now? The Kruskal algorithm is, it says choose the minimum weight edge. So like this one. Once we chooses this one, I chooses this one, okay, with the weight one. Now, except this one, choose which have the minimum weight. So this one. Okay. So it is already connected. So I chooses that edge. Okay. But it is in a connected form. That's why I just wrote here. Okay. That's why I just wrote here. Now choose the minimum weight. So this is, we have the minimum weight. Okay. So, okay, we chooses this one. We chooses that one. Now, already whatever we chooses, except that choose the minimum weight. So this we have, this have the minimum, or this we have. Okay. So let's choose this one. We cannot choose this one because once you add that, it will become a cycle. So let's choose this one. So we chooses this one. This is the we have. So see that it is in separated form, but it doesn't matter. We just choose that edges. Once we choose, the finally will connect that one by one. Now, except this one, which have the minimum. So this is the 2, yeah. So this one have the minimum. So choose this one edge. Now this is the separated form, no? Now, except this all whatever we chooses, choose the except of that. So which have the minimum. Now this one have. So choose this we have. So 3. So now we are done because all vertices we have written here. So this is the spanning tree. If you now count, this is the same we have. But maybe differ also, but the cost will be the same. So this is the Kruskal algorithm. Choose the edges of the minimum weight one by one, do this. Once you complete it, the final, and then you will see that those edges are actually in the connected form, and that will tell you the spanning tree. So this is the minimum cost spanning tree, and this is the algorithm, whatever I am discussing here. This is the Kruskal algorithm. And this is the way to find the minimum cost spanning tree by the Kruskal algorithm. Okay.
Okay, sir.
So that's all. I think for this week 11, the Kruskal we discussed. So whatever the algorithms we have, the first we have the first one is longest path shortest. After the longest shortest, we have Warsaw algorithm. Warsaw algorithm is to find the transitive closure. But if you see that in lecture, it is not much discussed. So that's why you can remove that one. Otherwise, Warsaw algorithm is for to find the transitive closure. And then Dijkstra algorithm is there. Dijkstra algorithm is for shortest path. Single source, you can say single source single source shortest path, but positive weight. Okay. And the next is Bellman-Ford algorithm, that is allows for the shortest path, but negative weight also. Here is the negative weight is also allowed. Weight. Okay. But the thing is, there should be no negative cycle. There should be no negative cycle in that graph. And then there is next is Floyd-Warshel algorithm, that is for all source, you can say all source or from all to all. That algorithm is actually give the shortest path from all vertex to all vertex. Means if you see that the finally if you see that so in that the finally whatever you will get, no, there the final matrix, whatever the final matrix you will get, it will give the all vertex to all vertex shortest path. The entries, if you check that, whatever the entries you will get, no, if you match with that vertex to vertex, you will get the shortest path or what is the length of the shortest path. So Floyd-Warshel algorithm is from all source vertex or all vertex to all vertex shortest path is. This is for also shortest path. And that is I am suggesting you please watch that lecture. That's why I am unable to finish here. And also we did. So the next is, this is third one. This is the fourth one is the Prism algorithm. I think so. That is the correct English. Prism. I'm saying Prim's algorithm. Prim's. This is Prism. I'm saying Prim's algorithm is there. Prim's algorithm. This is for the minimum cost spanning. Okay, minimum cost spanning tree. And the last one is the Kruskal. Kruskal's algorithm. This is also for minimum cost spanning tree. Okay, so these are. So I'm suggesting you at least these two should be clear, because as the purposely, if you see that these are the easier one or this is the easily candor or the extra, you can see Bellman you can skip, because as if you see in the end term exam it will be very difficult, because these two Floyd and Bellman will take more time, so you can skip the question related to this one. Or if it is given, if the question will be given,
we can have negative and positive.
in the extra only the positive weight is there. Bellman and Warshel related question you can skip, because there is a less chance to ask. And the extra you can see in the first in the 10th lecture. I'm saying for the related question which may ask in the same exam, means cover or minimum vertex cover or graph coloring or edges, vertices, adjacency matrix, BFS, DFS,
Sir, can
spanning tree. Sorry.
so algorithm be used for cycles?
What is sorry? Cyclic? Am I audible?
Yes, sir, you are audible, sir.
Okay. So
Sir,
the top.
Sir, actually, I have one doubt related to exam. So,
Okay.
what is going to the weightage of weeks in the exam?
So
Week by
like we have the quizzes, no? So you can give the weight for at least graph is, you can say that 25% for the graph theory or 30% you can give the graph, or more than the graph, and one lecture is remain from the calculus. So if you add those all, maybe 35% or 40% you can give the weightage, at least 30 to 40, 35 you can at least you can give weight for this one, and the rest all you can give the weightage for 1 to 4 and 6 to 4 to 8, like this you can.
Yes,
So
sir.
it's simple. Yeah, you can. It is obvious that the more weightage is which we have and discussed for the graph theory and the that calculus, the last lecture, and then rest all for the week 1 to 4 and 4 to 8. And important topics I am suggesting you for the, you can skip the Belmont and Floyd-Warshel algorithm. The Prism and Kruskal, you can see that these are the important, you can see, and also longest path and that topological sorting, you can think that is one, and then in week 10 you can BFS, DFS, and BFS, DFS, and then graph coloring, minimum vertex cover, independent set. These are some important topic you can think. And adjacency matrix is also one.
Thank you, sir.
So these are the important topic you can think. You can skip Bellman and Floyd. This from my side I'm saying.
Okay, sir.
Okay, that's all. Please let me know if anyone have doubt, or I'm now going to close the session also. So anyone have doubt, please let me know.
No, sir. Currently, I don't doubt. I just completed it to 1.7.
Okay,
Thank you,
so
sir,
please
for the
watch the
session.
lecture. Please watch the lecture. Then may watch. I'm suggesting you please go through that whatever we have this one if you want on the portal video lecture. Sorry, in the portal these 2 sessions. These are the important session, and also in week 10 also we have. Okay, we have in week 10 we have also some standard sessions in that very nicely have explained everything I have explained. So there you can see these 2 sessions also we have to clear the very
Sir, does
the perfect
Dijkstra
way.
algorithm, can they be used for the cycles? When there's a cycle in the graph.
So yeah, if there is a cycle, still the Dijkstra will not work, no? And also in the side there will be no cycle. If the Dijkstra is there and cycle is happening, then you cannot get the shortest path with respect to using the Dijkstra. So you can skip the cycle thing. Even whatever the algorithm is given, you can skip the cycle thing for the negative or positive. Okay. Cycle is not generally discussed in the, you cannot think in the case of weight or spanning also. A spanning set also don't have the cycle. And to apply the Belmont or Warshel, Floyd-Warshel, there is no negative cycle. And the Dijkstra also don't have cycle. In those cases you can think. Okay.
Request, sir.
Huh?
Sir, we are finished with week 11. That means we are finished with the syllabus for end term of Maths 1.
Yes, yes.
So can we start a revision from next lectures?
Next lecture, revision from next lecture means from first.
Means like just like we prepared for our qualifiers, then we had the revision sessions with TS as well and with instructors as
Yeah,
well.
that yes, those will all be soon we will get the updated. We'll get in the calendar when the revision session will be. I think it will be from 25, 26, maybe 20. Yeah, it may be. We'll get that soon. From 26 or 25, then 28, and then 30 will be probably. These are the revision sessions from instructor. Probably, I'm just saying. I'm just maybe from 25 because Friday we have, and then Monday, and then Wednesday. That's the one we will make it. And from the TS, you will get the PYQ and the PYQ, previous question discussion thing will happen. So that would be probably from, okay. So 3 we have, na? So from Thursday,
End term
we can
exam
expect.
duration is 1.5 hours, but the questions will be still 13 to 14.
13 to 14, yeah. So yeah, 13 to 14, some question will be some have parts. So that's why I'm saying some, suppose there are 13 questions, but some question have some parts. So if you count that, that will be different, and like it will be 20, 20, 22, but in the form of that particular, it will be question, you can say there are 13 to 14, but in the parts, if it is the parts, it is divided in the parts, then it may reaches to 20 also, but that is not tough. That is for your convenience, so that you may get the marks like that. It is break down in the parts. Okay, so that
Yes.
your marks will not deducted, and if you know the concepts, you can do that particular parts question and get the marks. Okay, so and the revision session from the PYQ sessions you can expect from Thursday, and then whatever the days we have, or sorry, this Thursday 25, 26, sorry, 24, 26. Still you will get soon the mail, and the upcoming, like from Monday or from Wednesday or Thursday, you will start getting the revision and PYQ sessions. Okay, at least 2 to 3 older QPs will be discussed. Okay.
Yes.
Okay.
Okay, sir. Thank you.
Okay.
Okay,
Sorry.
sir. Thank you.
Yeah. Thank you so much. Good night to all of you.
Good night.
Good night, sir.